For our second video lecture, we're going to focus on x-intercepts and also average rate of change. So just to review x-intercepts, they're the same. We sometimes call them informally zeros, right? The zeros of a function. So if I have f of x equals 2x minus 5, I want to find the x-intercepts. I want to set 2x minus 5 equal to 0. All right, so then I would say 2x equals 5. And then I would divide by 2 on both sides, and I would say that the x-intercept is x equals 2.5. Okay? So x equals 2.5 produces an output of y equals 0, which means that on our graph, when y is 0, that means we're moving not at all in the y direction and only moving in the x direction, which puts us on the x-axis, which is why we call this an x-intercept. Okay, so if we look at the graph, here it is. It's a nice line with a slope of 2, and it crosses through the axis at x equals 2.5. Okay, as we can see here, 2.5 comma 0. All right, so let's look at another one, square root x minus 3. If we want to find the x-intercept of this, we're going to set square root x minus 3 equal to 0. So then we want square root x to be equal to 3. So now how do we solve for x? We're going to square both sides of this function, and we're going to get x equals 9. Again, x equals 9 is the input that's going to produce an output of y equals 0, which means x equals 9 is our x-intercept. Again, we can see that on the graph. Okay, here's our square root function. It crosses through at 9 comma 0 because that is the x-intercept. Okay? So let's look at a harder example, and I want to use this example to also review domain, which is what we covered in our live class today. So when we think about the domain of this function, we first see that we cannot divide by 0. So we see that would happen if we had x equal to 5 or 7. So we would say x cannot be 5 and x cannot be 7. And then we can also look up here to this portion of the function. Okay, we know we cannot square root a negative number, so we need to think about what inputs would cause us to make a negative number. So for example, we know that x cannot be 3, right, because square root of 3 minus 4 is no good, negative. Okay, we know that x cannot be 2, because square root of 2 minus 4 would be also a negative number. We can't square root a negative number in the real numbers. Okay, x cannot be 1, because square root of 1 minus 4 would be negative. Okay, you get the picture. Okay, x can be 4 because 4 minus 4 is 0. Okay, and the square root of 0 is just 0. And in fact, x can be anything bigger than or equal to 4, right? So we might write our domain as, our domain is 4. Okay, it starts at 4. We can include 4, so we do these closed brackets. Okay, it goes from 4 to 5, but it cannot be 5, so we do not include 5. Then it goes 5 to 7, but it cannot be 7, so we don't include 7, and then we go 7 to infinity. Okay. Somewhere within this interval, we are going to have our x-intercept. Okay, so I'm going to go ahead and clear out some of this stuff. So we want to know when this function is going to be equal to 0. All right. Now this is going to happen when the numerator of the function is equal to 0. So what we're going to do is we are going to set square root x minus 4 minus 2 equal to 0. Square root x minus 4 minus 2 equals 0. And let's solve this. We get square root x minus 4 equals 2. All right. And then that means that, well, so what's our next step? How are we going to undo this square root sign? The inverse operation is squaring both sides. So now we have x minus 4 equals 4, and then we see that x equals 8. Okay, that is our x-intercept. Because when we plug in x equals 8 to this function, what we're going to get is square root 8 minus 4 minus 2, which equals square root 4 minus 2, which equals 2 minus 2, which equals 0. All right, so we have our 0 in the numerator, and the denominator is going to be some non-zero number. 0 divided by any non-zero number is just going to be equal to 0. So our x-intercept is equal to 8, and that would fall within our interval. That falls between 7 and infinity. 8 is in here, right? equals 8 is our x-intercept, and that just falls right in this interval, right? So our domain is 4 to 5, 5 to 7, 7 to infinity, and then our x-intercept happens at x equals 8, which happens in this part of the domain. So let's look at the graph, okay? So we know that x cannot be 5, so we see what we call a vertical asymptote at x equals 5, and we'll review that terminology later on in this quarter. And then we also see that x cannot be 7, another vertical asymptote there. We also see that our domain starts at x equals 4, as we said it would, right? 4 to 5, 5 to 7, 7 to infinity. So it starts at 4. And then we see that x-intercept happens at x equals 8. Okay, so it's always good to bring graphical context back into our examples, right? So now we're going to move on to average rate of change. Our essential question is, how can we compare the steepness of different curves? So we're going to do another algebra 2 recall here, algebra 2 recall. Find the average rate of change of the following functions on the interval from 1 to 3. Now, this is an interval of x values. X equals 1 to x equals 3. So see if you can remember how to find the average rate of change given a couple x values. So you can pause the video, attempt to find the average rate of change of these three functions. So once you've tried it, you can unpause and just watch me work through these. So what we're going to do is all three of these calculations are going to involve 3 minus 1 on the bottom. Okay, because 3 minus 1, this represents our change in run, right? It's our change in x. And since x is our horizontal value, we call that horizontal change the run of the function, right? So what do we need on top? Well, we need the change in rise, which means on top, we need the change in y, right? The bottom is change in x. Okay, this is going to ultimately give us our change in rise over our change in run. So we need to know what our outputs, our y values are, right? So how can we do that? Well, we can just plug our x values right into the function. So what is f of 3? Okay, we're focusing on this one at first, okay? What is f of 3? Well, that's just going to be 3. And then what's f of 1? Well, that's just 1, right? Okay, now let's focus on this one. Okay, for this one, we have to use the function x squared, so we're going to have 3 squared on top minus 1 squared, right? And then finally, we'll focus on this one. Okay, this one, we're plugging in x equals 3, x equals 1, so we're going to have 3 cubed minus 1 cubed, okay? And now we need to simplify this and get our final answer for our average rate of change, okay? So 3 minus 1 over 3 minus 1 gives us an average slope of 1. Remember, this is 3 squared minus 1 squared. And then this is 3 cubed minus 1 cubed. Okay? So we can see the average rate of change of x squared from x equals 1 to x equals 3 is equal to 4. And the average rate of change of x cubed from x equals 1 to x equals 3 is 13. All right? And then obviously for y equals x, it's just a straight line, right? So we're just really looking at the slope of this, which is 1. All right? So here's a couple more for you to try, or a few more for you to try. You're going to find the average rate of change of x squared, x cubed, and x to the 5th from on the interval x equals 0 to x equals 0.5. Right, remember, this is what this means. So pause the video and give that a shot, and then I'll show you the answers in a second. Okay, here they are. So I have this 0.25. Where did I get that? That's just 0.5 squared minus 0 squared, right? This is 0.5 cubed minus 0 cubed. And then this is 0.5 to the 5th minus 0 to the 5th, right? And then we can see these in fraction form. It's just 1/2, 1/4, and 1/16. All right? We didn't really talk about this on the last slide, but what we can see is this is obviously a curve. And what this is doing, since a curve has a constantly changing slope, this is giving us the average slope, right? The average slope from 1 to 3. That is what average rate of, or from 0 to 3, sorry. That is what average rate of change does for us, right? So we can see the average slope here. Okay, that was equal to 1/4, and then the average slope, the change in rise over change in run, is 1 over 16. Okay. So the big idea with average rate of change is that it allows us to describe steepness of curves which have constantly changing steepness, right? So straight lines, we always talk about slope because we can just talk about the slope of the line and that tells us how steep it is. But since a curve has a constantly changing slope, well, we can't really talk about that changing slope very easily right now, but what we can do is talk about the average slope by just drawing a line through the 2 points and finding the slope of that line, which is what we did up here. We did the change in rise over the change in run, and that gave us the slope of this line. Okay, this x cubed has a constant. We can see that it's steep, and then it's flat, and then it's steep, 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 and just keeps getting steeper. That's what happens to x cubed. And so we can't really talk about that changing steepness right now. But what we can do is talk about the average rate of change on an interval. So in this case, we did from 1 to 3. Okay, 1 to 3 has a change in run of 2, and then we just plugged in those 2x values to find our change in rise, and then we did change in rise over change in run to get the average slope. So you can see that x squared seems to be steeper than x, and x cubed seems to be the most steep on the interval from 1 to 3. But if we look at these three, okay, x squared seems to be more steep than x cubed than x to the 5th, which is actually really, really flat from 0 to 0.5, right? And so we can compare the steepness of these three functions by looking at different intervals. Okay, we can see that this function starts more steep than these two, but I think that you could see that x cubed and x to the 5th are going to become much more steep over time. So if we look at later intervals, that's what we would see. So this is just our general average rate of change formula. Okay, you can think of this as being like y2 minus y1 over x2 minus x1. That's another way you might have seen this. Okay, but we're just going to take our x value b and our other x value a and plug it into our function to get our two y values. So that we can get the change in rise over the change in run and then the average slope. Go ahead and pause if you want to make sure you get all of this down in your notes. So then we can even do this from a table, and it doesn't have to be x and y values. It's just inputs and outputs. So you should recognize the t value as the input here, and then the w of t is the output. So we're really just going to do the change in output over change in input. So first we'll do 0 to 9. So we're going to do from t equals 0 to t equals 9. So we always want to have our inputs on bottom because that's our change in run. So we have 9 minus 0. And then on top, we're just going to do w of 9 minus w of 0. All right. So then what's w of 9? That's just right here. It's 61.8 minus. Okay, and then we have w of 0 is 55. And then we're going to do that over what's 9 minus 0? That's just 9. Okay, so this is going to be 6.8 divided by 9. Let's get an approximation for that. So I'm getting that is 0.75 repeating. And then because this is a function that includes units, we should include the units in our answer. So we have that our output is a change in degrees Fahrenheit, and our input is minutes. So we would say that this is 0.75 repeating degrees per minute. So on average, the temperature is increasing by 0.75 degrees every minute from minute 0 to minute 9. That's what we just figured out. Okay, let's do t equals 4 to t equals 15. So we're going to do w of 15 minus w of 4 over 15 minus 4. So w of 15 is just 67.9, and then w of 4 is just 57.1. So then 67.9 minus 57.1 is going to be 10.8 divided by 11. So that's really close to being 1. Let's get an exact approximation here. Okay, it's 0.98 about. 0.98, and again, this is degrees per minute. So from minute 4 to minute 15, the temperature was increasing by about 1 degree every minute. And we can see this temperature is constantly increasing, and this allows us to find on average how quickly it's increasing. Okay, last example here, or last two examples. You're driving and your speedometer is broken, but your odometer works. Can you determine your average speed? So if your speedometer is broken, that means you can't see your speed as you're driving, right? But your odometer tells you how many miles you've driven, right? So when you first start driving, let's say your odometer reads 80,125 miles, right? That means that at that point, that's how much mileage you had put on your car, okay? 10 minutes later, it now reads 80,140 miles, okay? Can you determine your average speed? Try to do that now by yourself, and then unpause when you're ready to see it worked out. So all we have to do here is use average rate of change, right? So at minute 10, this was our odometer reading. At minute 0, this was our odometer reading. Our change in mileage is 15 miles, and then that took 10 minutes. And if we just take our 15 over 10 and multiply by 6 over 6, that's going to give us 90 miles in 60 minutes, which tells us that we were going on average 90 miles an hour. So hopefully we're like on an empty highway or something like that, where it might be okay to drive that fast. That's pretty fast, faster than I drive. Okay, but we were able to use our odometer to do an average rate of change calculation and figure out our average speed. Okay, so what if we do the average rate of change of our speed? So now we have a function s of t that tells us our speed. Okay, and then this is our time that has passed. So let's find our average rate of change from t equals 0 to t equals 3. So we're going to do s of 3 minus s of 0 over 3 minus 0. And again, we want to include units here. So s of 3 is just equal to 10, and s of 0 is just equal to 15. So then that's going to give us negative 5 over 3, and then this is feet per second, and then, okay, so that's feet per second divided by seconds, okay? So then that's negative 5 over 3 feet per second squared, which is just what we call acceleration. Okay, so the average rate of change of this on this table is going to tell us how we are accelerating. And we can see that from minute 0 to minute 3, we were actually slowing down. We were going 15 feet per second, and now we're going 10 feet per second. So that's why we end up with a negative number here. And on average, our speed was decreasing by 5/3 feet every second, right? Feet per second every second. That's how quickly we are slowing down. Okay. So that's all I have. You will now have some practice problems you can work on your problem set.